This creature is a wonder of life. A voracious predator, this male has lived underwater for nearly 5 months, feeding, growing, preparing for this moment. He's about to undertake one of the most remarkable transformations in the natural world. From aquatic predator to master of the air. Life of a dragonfly is amongst the most energetic in nature. Dragonflies are the most remarkable animals. You can see their incredible agility in flight just watching them skim across the surface of this pond. They can pull 2.5 G in a turn. And they can fly at 15 miles an hour, which is fast for something that big. They've been around on Earth since before the time of the dinosaurs, and in that time they've been fine-tuned by natural selection to do what they do, which is to catch their prey on the wing. So dragonflies are beautiful pieces of engineering. They're intricate, complex machines. But is that all they are? Because once their brief lives are over, their vitality will be gone. And this raises deep questions. What is it that makes something alive? And how did life begin in the first place? So, what is the difference between the living and the dead? What is life? The most isolated regions of the Philippines to visit the remote hilltop town of Sagada. It's a 2-day drive from the capital Manila over some of the country's roughest roads that wind their way 1,500 metres up into the hills. This is a place where the traditional belief is that mountain spirits give us life and that our souls return to the mountain when we die. And where the people who live here still imagine that the spirits of the dead walk among the living. Tonight is November the 1st, and here in Sagada, in fact across the Philippines, that means that it's the Day of the Dead. That's the day when people come to this graveyard on a hillside and, well, celebrate the lives of their relatives. people light fires to honour and warm the departed, inviting their souls to commune with them. No matter how unscientific it sounds, this idea that there's some kind of soul or spirit or animating force that makes us what we are and that persists after our death is common. Virtually every culture, every religion has that deeply held belief. And there's a reason for that, because it feels right. I mean, just think about it. It's hard to accept that when you die, you will just stop existing, and that your life, the essence of you, is just really something that emerges from an inanimate bag of stuff.
Mamati ay wala ng spirits da. Kanayon ay kakadwamimot lang. At sabi ng amok ay kakadwamimot lang da idaas ng pag-adinan ano ka kakalkalimi da ay silently.
That these people feel not only that they come and celebrate the lives of their relatives, but they're coming in some sense to communicate with them. Their relatives, even though their physical bodies have died, are still in some sense here. And when you think about it, that's not so easy to dismiss. I mean, if we are to state that science can explain everything about us, then it's incumbent on science to answer the question, what is it that animates living things? What is the difference between a piece of rock that's carved into a gravestone and me? For millennia, some form of spirituality has been evoked to explain what it means to be alive and how life began. It's only recently that science has begun to answer these deepest of questions. In February 1943, the physicist Erwin Schrödinger gave a series of lectures in Dublin. Now, Schrödinger is almost certainly most famous for being one of the founders of quantum theory, but in these lectures, which he wrote up in this little book, he asked a very different question: what is life? And right up front on page 1, he says precisely what it isn't. It isn't something mystical, says Schrödinger. There isn't some magical spark that animates life. Life is a process. It's the interaction between matter and energy described by the laws of physics and chemistry, the same laws that describe the falling of the rain or the shining of the stars. So the question is, how is it that this magnificent complexity that we call life could have assembled itself on the surface of a planet which itself formed from nothing more than a collapsing cloud of gas and dust? To Schrödinger, the answer had to lie in the way living things process one of the universe's most elusive properties: energy. Energy is a concept that's central to physics, but because it's a word that we use every day, its meaning has got a bit woolly. I mean, it's easy to say what it is in a sense. I mean, obviously this river has got energy because over the decades and centuries it's cut this valley through solid rock. But while this description sounds simple, in reality, things are a little more complicated. For me, the best definition is that it's the length of the space-time core vector in the time direction, but that's not very enlightening, I'll grant you that. Over the years, the nature of energy has proved notoriously difficult to pin down, not least because it has the seemingly magical property that it never runs out. It only ever changes from one form to another. Take the water in that waterfall. At the top of the waterfall it's got something called gravitational potential energy, which is the energy it possesses due to its height above the Earth's surface. See, if I scoop some water out of the river into this beaker, then I'd have to do work to carry it up to the top of the waterfall. I'd have to expend energy to get it up there, so it would have that energy as gravitational potential. Even do the sum sphere. Half a litre of water has a mass of half a kilogram. Multiplied by the height, that's about 5 metres, and the acceleration due to gravity is about 10 metres per second squared. So that's half times 5 times 10 is 25 joules. So I'd have to put in 25 joules to carry this water to the top of the waterfall. Then, if I emptied it over the top of the waterfall, then all that gravitational potential energy will be transformed into other types of energy. It's sound, there's pressure waves in the air, there's the energy of the waves in the river, and there's heat, so it'll be a bit hotter down there because the water's cascading into the pool at the foot of the waterfall. But the key thing is, energy is conserved, it's not created or destroyed. So because energy is conserved, if I were to add up all the energy in the water waves, all the energy in the sound waves, all the heat energy at the bottom of the pool, then I would find that it would be precisely equal to the gravitational potential energy at the top of the falls. What's true for the waterfall is true for everything in the universe. It's a fundamental law of nature, known as the first law of thermodynamics. And the fact that energy is neither created nor destroyed has a profound implication. It means energy is eternal. The energy that's here now has always been here, and the story of the evolution of the universe is just a story of the transformation of the energy from one form to another, from the origin of the first galaxies to the ignition of the first stars and the formation of the first planets. Every single joule of energy in the universe today was present at the Big Bang 13.7 billion years ago. Potential energy held in primordial clouds of gas and dust was transformed into kinetic energy as they collapsed to form stars and planetary systems, just like our own solar system. In the sun, heat from the collapse initiated fusion reactions at its core. Hydrogen became helium. Nuclear binding energy was released, heating the surface of the sun, producing the light that began to bathe the young Earth. And at some point in that story, around 4 billion years ago, that transformation of energy led to the origin of life on Earth. 350 kilometres south of Sagada. This is Lake Tal. Despite its sleepy, languid appearance, this landscape has been violently transformed by energy.
I usually think of a pointy, fiery mountain with a little crater in the top. Probably a bit like that one. But actually this entire lake is a bloody crater of a giant volcano. It began erupting only about 140,000 years ago. And in that time, it's blown 120 billion cubic meters of ash and rock into the Earth's atmosphere. And this crater is 30 kilometers across and in places 150 meters deep. And that's a cube of rock, 5 kilometers by 5 kilometers by 5 kilometers, just blown away. It's a big volcano.
Tal Lake is testament to the immense power locked within the earth at the time of its formation. Since the lake was created, a series of further eruptions formed the island in the centre. And at its heart is a place where you can glimpse the turmoil of the inner earth, where energy from the core still bubbles up to the surface. Producing conditions similar to those that may have provided the very first spark of life. And the water in this lake is different from drinking water in a very interesting way. See, if I test this bottle of water with this, which I call a universal indicator paper, then you see immediately that it goes green. And that means that it's completely neutral. It's called pH 7 in the jargon. Then, what happens when I test the water from the lake? Now the indicator paper stays orange. In fact, it might have gone a bit more orange. So that means that this is acid. It's about pH 3. At the most basic level, the energy trapped inside the earth is melting rocks. And when you melt rock like this, you produce gases. A lot of carbon dioxide. In the case of this volcano, a lot of sulfur dioxide. Now, sulfur dioxide dissolves in water and you get H2SO4, sulfuric acid. Now, what do I mean when I say that the water is acidic? Well, water is H2O, hydrogen and oxygen bonded together. But actually, when it's liquid, it's a bit more complicated than that. It's actually a sea of ions, so H plus ions, that's just single protons, and OH minus ions, that's oxygen and hydrogen bonded together, all floating around. Now when something's neutral, when the pH is 7, then that means that the concentrations of those ions are perfectly balanced. When you make water acidic, then you change the concentration of those ions. And to be specific, you increase the concentration of the H plus ions, of the protons. So this process of acidification has stored the energy of the volcano as chemical potential energy. The volcano transforms heat from the inner earth into chemical energy and stores it as a reservoir of protons in the lake. And this is the same way energy is stored in a simple battery or fuel cell. These bottles contain a weak acid and are connected by a semi-permeable membrane. Passing an electric current through them has a similar effect to the volcano's energy bubbling up into the lake. It causes protons to build up in one of the bottles.
You can think of it, I suppose, like a waterfall where the protons are up here waiting to flow down. And all you have to do to release that energy and do something useful with it is complete the circuit, which I can do by just connecting a motor to it. There you go. Look at that. That's the protons cascading down the waterfall and driving the motor around. Actually works. Remarkable, actually.
Now the fuel cell produces and exploits its proton gradient artificially, but there are places on Earth where that gradient occurs completely naturally. Here, for example. So we've got the proton reservoir over there, the acidic volcanic lake. If you look that way, there's another lake. And the reaction of the water with the rocks on the shore make that lake slightly alkaline, which is to say that there's a deficit of protons down there. So here's the waterfall, the reservoir of protons up there, the deficit down there. If you could just connect them, then you'd have a naturally occurring geological fuel cell. And it's thought that the first life on our planet may have exploited the energy released in those natural proton waterfalls.
These are pictures from deep below the surface of the Atlantic Ocean, somewhere between Bermuda and the Canaries. And it's a place known as the Lost City. You can see why. Look at these huge towers of rock, some of them 50, 60 metres high, reaching up from the floor of the Atlantic and into the ocean. And it's what's known as a hydrothermal vent system. So these things are formed by hot water and minerals and gases rising up from deep within the Earth. But the reason it's thought that life on Earth may have begun in such structures is because these are a very unique kind of hydrothermal vent called an alkaline vent. And about 4 billion years ago, when life on Earth began, seawater would have been mildly acidic. So here is that proton gradient, that source of energy for life. You've got a reservoir of protons in the acidic seawater and a deficit of protons around the vents. And the vents don't just provide an energy source, they're also rich in the raw materials life needs. Hydrogen gas, carbon dioxide, and minerals containing iron, nickel, and sulfur. But there's more than that. So these vents are porous, there are little chambers inside them, and they can act to concentrate organic molecules. Inside these vents, you've got concentrated building blocks of life trapped inside the rock. And you've got that proton gradient, you've got that waterfall that provides the energy for life. So this could be where your distant ancestors come from. The places like these could be the places where life on Earth began. The
first living things might have started out as part of the rock that created them. Simple organisms that exploited energy from the naturally occurring proton gradients in the vents. And we think this because living things still get their energy using proton gradients today. Deep within ourselves, the chemistry the first life exploit events is wrapped up in structures called mitochondria, microscopic batteries that power the processes of life.
This is a picture of the mitochondria from a little brown bat. This is a picture of mitochondria from a plant. It's actually a member of the mustard family. This is a picture of mitochondria in bread mould, and this of mitochondria inside a malaria parasite. So the fascinating thing is that all these animals and plants, and in fact virtually every living thing on the planet, uses proton gradients to produce energy to live. Why? Well, the answer is probably because all these radically different forms of life share a common ancestor. And that common ancestor was something that lived in those ancient undersea vents 4 billion years ago, where naturally occurring proton gradients provided the energy for the first life. So if you're looking for a universal spark of life, and this is it. The spark of life is proton gradients. In those 4 billion years, that spark has grown into a flame. And a few simple organisms clustered around a hydrothermal vent have evolved to produce all the magnificent diversity that covers the Earth today.
On Earth is so diverse, it covers so much of the planet that you can find places like this lake, and it's effectively its own sealed ecosystem. It's saltwater, it's connected to the sea, but it's only connected through small channels through the rock. So that means that the marine life in here is effectively isolated. This is the golden jellyfish, a unique subspecies only found in this one lake, on this one island, in the tiny Micronesian Republic of Palau. They used to live like most jellyfish, cruising the open ocean, catching tiny creatures, zooplankton, in their long tentacles. But today, their tentacles have all but disappeared, because the golden jellyfish have evolved to do something that very few other animals can do.
It really is incredible. There are, I want to say, millions of jellyfish, as far as you can see, all the way down till the light vanishes. There are jellyfish, and you can see them congregating in the sun. If you go over there to bathe, there are just none, and then in this pool of light beneath the sun, there are millions of them. beautifully elegant things just floating around. I'm not being unduly hyperbolic, it's quite remarkable.
This lake is home to over 20 million jellyfish, whose success comes down to a remarkable adaptation. Their bodies play host to thousands of other organisms, photosynthetic algae that harvest energy directly from sunlight. Jellyfish engulf the algae as juveniles, and by adulthood, algal cells make up around 10% of their biomass. Grouped into clusters of up to 200 individuals, they live inside the jellyfish's own cells. The golden jellyfish uses algae to get most of its energy from photosynthesis.
The ones at the surface are gently, they're gently turning. And the reason they do that is to give all their algae an equal dose of sunlight. So they're quite democratic creatures, just making sure they get as much food as they can. They just come up to you, jumping around, photosynthesizing. They tell me they don't sting, but I'm sure I've got a tingling finger.
And it's not just their anatomy that's adapted to harvest solar energy. Every morning, as the sun rises, the jellyfish begin to swim towards the east. And as the sun tracks across the sky, they move back again towards the west, where they spend their night. So the jellyfish have this beautiful, intimate and complex relationship with the position of the sun in the sky. As sunlight is captured by their algae, it's converted into chemical energy. Energy they use to combine simple molecules, water and carbon dioxide, to produce a far more complex one: glucose. Once absorbed by the jellyfish, glucose and other molecules not only power their daily voyage across the lake, they provide the basic building blocks the jellyfish use to grow the elegant and complex structures of their bodies. So the jellyfish, through their symbiotic algae, absorb the light, the energy from the sun, and they use it to live, to power their processes of life. And that's true, directly or indirectly, for every form of life on the surface of our planet. But things are a little bit more interesting than that, because energy is neither created nor destroyed. So life doesn't eat it somehow, it doesn't use it up, it doesn't remove it from the universe. So what does it do? To understand how energy sustains life, you have to understand exactly what happens to it as the cosmos evolves. In the first instance after the Big Bang, there was nothing in the universe but energy. As it changed from one form to another, galaxies, stars and planets were born. But while the total amount of energy in the universe stays constant, with every single transformation, something does change. The energy itself becomes less and less useful. It becomes ever more disordered. And you can see this process in action as energy from the sun hits the surface of the earth. So think about this sand on the beach. It's been under the glare of the sun all day. It's been absorbing its light, which has been heating it up. And now the sun is dipping below the horizon, and then the sand is still hot to the touch because it's re-radiating all the energy that it absorbed as heat back into the universe. And the key word there is all the energy. See, if it didn't do that, then it would just gradually heat up day after day after day, and eventually, I suppose, the whole beach would melt. So what's changed? Well, it's the quality of the energy, if you like. I mean, think about it. If as much energy is coming back off this sand now as it absorbed from the sun, then it should be giving me a suntan. I should need sun cream if I sit looking at this beach all night, and obviously I don't. The difference is that this energy is of a lower quality. It can do less. It's heat, which is a very low quality of energy indeed. So what the sand's done is take highly ordered, high quality energy from the sun and convert it to an equal amount of low quality, disordered energy. This descent into disorder is happening across the entire universe. As time passes, every single joule of energy is converted into heat. The universe gradually cools towards absolute zero, until with no ordered energy left, the cosmos grinds to a halt, and every structure in it decays away. Yet whilst the universe is dying, everywhere you look, life goes on. It's a deep paradox that Schrödinger was well aware of when he wrote his book in 1943. How can it be, like Schrödinger, that the living organism avoids decay? In other words, how can it be that life seems to continue to build increasingly complex structures when the rest of the universe is falling to bits, is decaying away? Now, that's a paradox, because the universe is falling to bits. It is tending towards disorder. That is enshrined in a law of physics called the second law of thermodynamics. And I think most physicists believe that it's the one law of physics that will never be broken. To understanding how life obeys the laws of thermodynamics is to look at both the energy it takes in and the energy it gives out. This is a thermal camera, so hot things show up as red and cold things show up as blue. So what you're seeing here is that the chicken is hotter than its surroundings. Now, heat is a highly disordered form of energy. So the chicken is radiating disorder out into the wider universe. By converting chemical energy into heat, life transforms energy from an ordered to a disordered form, in exactly the same way as every other process in the universe. fact, every single human being generates 6,000 times more heat per kilogram than the sun. And it's by converting so much energy from one form to another that life is able to hang on to a tiny amount of order for itself, just enough to resist the inevitable decay of the universe.
So it's no accident that living things are hot, they export heat to their surroundings, because it's an essential part of being alive. The living things borrow order from the wider universe, and then they export it again as disorder. But it's not precisely in balance. They have to export more disorder than the amount of order they import. That is the content of the second law of thermodynamics. And living things have to obey the second law because they are physical structures. They obey the laws of physics.
Just by being alive, we too are part of the process of energy transformation that drives the evolution of the universe. We take sunlight that has its origins at the very start of time and transform it into heat that will last for eternity. So far from being a paradox, living things can be explained by the laws of physics, the very same laws that describe the falling of the rain and the shining of the stars. The dragonfly draws its energy from proton gradients, the fundamental chemistry that powers life. But the real miracles are the structures they build with that energy. Borrowing order to generate cells, arranging those cells into tissues, and those tissues into the intricate architecture of their bodies.
So we developed a quite detailed understanding of the underlying machinery that powers these dragonflies, and indeed all life on Earth. And whilst we don't have all the answers, it is certainly safe to say that there's no mysticism required. You don't need some kind of magical flame to animate these little machines. They operate according to the laws of physics, and I think they're no less magical for that.
Yet the dragonfly will only maintain this delicate balancing act for so long, because all living things share the same fate. Each individual will die, but life itself endures. This is because there's something that separates life from every other process in the universe. This is the Malaysian state of Sabah, on the northern tip of the island of Borneo. It's one of the most biodiverse places on the planet. Home to 15,000 plant species, 3,000 species of tree, 420 species of bird, and 222 species of mammals. Borneo Borneo's rainforests contain trees that are thought to live for more than 1,000 years. But the forest itself has existed for tens of millions of years. The reason it persists is because each generation of animal and plant passes the information to recreate itself onto the next generation. And that's possible because of a molecule found in every living thing. A molecule called DNA.
Now all I need to isolate my DNA is some washing up liquid, a bit of salt, and the chemist's best friend, vodka. Now, to get a sample of DNA, I can just use myself. If I just swirl my tongue around on the edge of my cheek, I'll dislodge some cheek cells into my saliva. I missed the test tube. There we are. It's a physicist doing an experiment. Then I add a bit of washing up liquid. Now what this will do is it will break open those cheek cells, and it will also degrade the membrane that surrounds the cell nucleus that contains the DNA. Salt will encourage the molecules to clump together. DNA is insoluble in alcohol, so you should get a layer of alcohol with the DNA molecules precipitated out. Yeah. There, can you see those strands of white? And so in that cloudy, almost innocuous looking solid are all the instructions needed to build a human being. So that is what makes life unique.
Only living things have the ability to encode and transmit information in this way. And the consequences of that profoundly affect our understanding of what it is to be alive.
This rainforest is part of the Sepilok Forest Reserve, and in here somewhere, some of our closest genetic relatives. There, can you see?
Orangutans are highly specialised for a life lived in the forest canopy. Their arms are twice as long as their legs, and all four limbs are incredibly flexible. Each one ending in a hand, whose curved bones are perfectly adapted for gripping branches. These adaptations are encoded in information passed down in their DNA.
You got a hat on. He has actually just put a hat on. This is the orangutan's genetic code. It was published in 2011, and there are over 3 billion letters in it. If I flip through it,
Look at that. Now it's composed of only 4 letters, A, C, T and G, which are known as bases. They're chemical compounds, they're molecules. And the way it works is beautifully simple. They're grouped into 3s called codons, and some of them just tell the code reader, if you like, how to start or where to start and when it's going to stop. It's fast. So you'd have a start and a stop. In between, each group of 3 codes for a particular amino acid. Now, amino acids are the building blocks of proteins, which are the building blocks of all living things. So you would just read along, you would find a start-stop, and then you would go along in 3s, build an amino acid, build amino acid, build amino acid, build amino acid, stitch those together into a protein, and if you keep doing that, eventually you'll come out with one of those. I mean, it's not that simple, of course, but the basics are there. This code written in there are instructions to make him.
To faithfully reproduce those instructions generation after generation, the orangutans, and indeed all life on Earth, rely on a remarkable property of DNA, its incredible stability and resistance to change.
Every time a cell divides, its DNA must be copied, and the genetic code is highly resistant to copying errors. The little enzymes, the chemical machines that do the copying, on average make only 1 mistake in 1 billion letters. I mean, that's like copying out the Bible about 280 times and making just 1 mistake.
That fidelity means adaptations are faithfully transmitted from parent to offspring. And so while we think of evolution as a process of constant change, in fact, the vast majority of the code is preserved. So even though we're separated from the orangutans by nearly 14 million years of evolution, what's really striking is just how similar we are. And those similarities are far more than skin deep.
Orangutans are surely one of the most human of animals, and they share many behavioural traits that you would define as being uniquely human.
They nurture their young for 8 years before they let them go on their own into the forest. In that time, the infants learn which fruits are safe to eat and which are poisonous, which branches will hold their weight and which won't.
And they can do all that because they have memory. They can remember things that happen to them in their life, they can learn from them, and they can pass them on from generation to generation.
And that deep connection extends far beyond our closest relatives. Because our DNA contains the fingerprint of almost 4 billion years of evolution.
If I draw a tree of life for the primates, then we share a common ancestor with the chimps and bonobos about 4 to 6 million years ago. And if you compare our genetic sequences, you find that our genes are 99% the same. You go back to the split with gorillas about 6 to 8 million years ago, and again, if you compare our genes, then you find that they are 98.4% the same. Back in time again,
common ancestor with our friends over there, the orangutans, then our genes are 97.4% the same. And you could carry on all the way back in time. You could look for our common ancestor with a chicken, and you'd find that our codes are about 60% the same. And in fact, if you look for any animal, like him, a little fly, or a bacteria, something that seems superficially completely unrelated to us, then you will still find sequences in the genetic code which are identical to sequences in my cells. So this tells us that all life on Earth is related, it's all connected through our genetic code. DNA is the blueprint for life, but its extraordinary fidelity means it also contains a story. And what a story it is. The entire history of evolution, from the present day all the way back to the very first spark of life. And it tells us that we're connected not only to every plant and animal alive today, but to every single thing that has ever lived. The question, what is life, is surely one of the grandest of questions. And we've learnt that life isn't really a thing at all. It's a collection of chemical processes that can harness a flow of energy to create local islands of order, like me and this forest, by borrowing order from the wider universe and then transmitting it from generation to generation through the elegant chemistry of DNA. And the origins of that chemistry can be traced back 4 billion years, most likely to vents in the primordial ocean. And most wonderfully of all, the echoes of that history, stretching back for a third of the age of the universe, can be seen in every cell of every living thing on Earth. And that leads to what I think is the most exciting idea of all, because far from being some chance event ignited by a mystical spark, the emergence of life on Earth might have been an inevitable consequence of the laws of physics. And if that's true, then a living cosmos might be the only way our cosmos can be.
Just remember you're a tiny little person on a planet in a universe expanding and immense. That life began evolving and dissolving and resolving in the deep primordial oceans by the hydrothermal vents. Our Earth, which had its birth almost 5 billion years ago, from out of a...
Stay with us on BBC HD. Our series Racing Legends continues next tonight with Olympic cycling hero Chris Hoy swapping bicycle for rally car to tell the story of Colin McRae.
These are the waters of Catalina, a tiny island 20 miles off the coast of Los Angeles, California.
These are kelp forests. They grow here in tremendous abundance because the waters here around Catalina are extremely rich in nutrients. That's because of the California current, which brings this beautiful, rich, cold water up from the depths of the Pacific and allows this tremendously rich ecosystem to grow. It's a remarkable place. Oh, look.
its burrow on the sea floor, the mantis shrimp is a seemingly unremarkable creature. It's not a real shrimp, but a type of crustacean called a stomatopod. I've come to see it because, in one way, the mantis shrimp is truly extraordinary. The way it detects the world. These are some of the most sophisticated eyes in the natural world. Each is made up of over 10,000 hexagonal lenses. And with twice as many visual pigments as any other animal, it can see colours and wavelengths of light that are invisible to me. These remarkable eyes give the mantis shrimp a unique view of the ocean. And this is just one of the many finely tuned senses that have evolved across the planet. Sensing, the ability to detect and to react to the world outside, is fundamental to life. Every living thing is able to respond to its environment. In this film, I want to show you how the senses developed, how the mechanisms that gather information about the outside world evolved, how their emergence has helped animals thrive in different environments, and how the senses have pushed life in new directions and may ultimately have led to our own curiosity and intelligence. Of Kentucky, the first stop on a journey across America that will take me from the far west coast to the Atlantic through the heart of the country. It's the animals that I'll find on the way that will illuminate the world of the senses. And I'm going to start by going deep underground. These are the Mammoth Caves in Kentucky. With over 300 miles of mapped passages, they're the longest cave system in the world. But this is also the place to start exploring our own senses. We're normally dependent on our sight, but down here in the darkness, it's a very different world. And I have to rely on my other senses to build a picture of my environment. Now it's completely dark in this cave. I can't see anything at all. You can see me because we're lighting it with infrared light, and that's at a wavelength that my eyes are completely insensitive to. So as far as I'm concerned, it is pitch black. And because it's so dark, your other senses become heightened, particularly hearing. It's virtually silent in here. But if you listen carefully, you can just hear the faint drop of water from somewhere deep in the cave system. You never hear that if the cave were illuminated. but you focus on your hearing when it's as dark as this. Now, as well as sight and hearing, we have, of course, a range of other senses. There's touch, which is really a mixture of sensations, temperature and pressure and pain. And then there are chemical senses, so smell and taste. And we share those senses with almost every living thing on the planet today because they date back virtually to the beginning of life on Earth. And even here, in water that's been collected from deep within a cave, there are organisms that are detecting and responding to their environment in the same way that living things have been doing for over 1 billion years. There it is. Now that is a paramecium. It may look like a simple animal, but in fact it's a member of a group of organisms called protists, and you'd have to go back around 2 billion years to find a common ancestor between me and the paramecium. Paramecia have probably changed little in the last 1 billion years. And although they appear simple, these tiny creatures display some remarkably complex behaviour. You can even see them responding to their environment. The cell swims around, powered by a cohort of cilia, tiny hairs embedded in the cell membrane. If it bumps into something, the cilia change direction and it reverses away. They're clearly demonstrating a sense of touch. Even though they're single-celled organisms, they have no central nervous system. They can still do what all life does. They can sense their environment and they can react to it. And they do that using electricity. The mechanism that powers the paramecium's touch response lies at the heart of all sensing in animals. And it's based on an electrical phenomenon found throughout nature. An electric current is a flow of electric charge, and for that to happen you need an imbalance between positive and negative charges. Now, usually in nature things are electrically neutral. The positive and negative charges exactly balance out. But there are natural phenomena in which there is a separation of electric charge. Thunderstorm, for example. As thunderclouds build, updrafts within them separate charge. The lighter ice and water crystals become positively charged and are carried upwards, while the heavier, negatively charged crystals sink to the bottom. This can create a potential difference, a voltage between the cloud and the ground of as much as 100 million volts. Now, nature abhors a gradient. It doesn't like an imbalance, and it tries to correct it by having an electric current flow. In the case of a thunderstorm, that's a bolt of lightning. the same process that governs the paramecium's behaviour, but on a tiny scale. In common with virtually all other cells, and certainly all animal cells, the paramecium maintains a potential difference across its cell membrane. And it does that, in common with a thunderstorm, by charge separation. By manipulating the number of positive ions inside and outside its membrane, the paramecium creates a potential difference of just 40 millivolts. So when a paramecium is just sat there, not bumping into anything, floating in this liquid, then it's like a little battery. It's maintaining the potential difference across its cell membrane, and it can use that to sense its surroundings. When it bumps into something, its cell membrane deforms, opening channels that allow positive ions to flood back across the membrane. As the potential difference falls, it sets off an electrical pulse that triggers the cilia to start beating in the opposite direction. That electrical pulse spreads around the whole cell in a wave called an action potential. And the paramecium reverses out of trouble. Now, this ability to precisely control flows of electric charge across a membrane is not unique to the paramecium. It actually lies at the heart of all animal senses. In fact, every time I sense anything in the world with my eyes, with my ears, or with my fingers, at some point between that sensation and my brain, something very similar to that will happen. Although the same electrical mechanism underpins all sensing, every animal has a different suite of sensory capabilities that is beautifully adapted to the environment it lives in. This is the Big Black River, a tributary of the mighty Mississippi in America's deep south. And these dark and murky waters are home to a ferocious predator. Even though it's impossible to see more than a couple of inches through the water, this predator has found a way to track down and catch its prey with terrifying efficiency. To help me catch one, I've enlisted the support of wildlife biologist Don Jackson.
You're going to wrestle it a bit, wrestle it out. He's going to go right here. Is he? There you go. You can bite. I'll show you the mouth of this thing. And I want you to see what the prey sees when he comes. Anything that'll fit in that mouth, he'll grab it.
Yeah.
And you can hold him if you just want to put your hands all the way under him. Come all the way. All the way. Hold him up close to you.
Yeah.
How about that?
Yeah. Well, this is the top predator in this river. This is a 25-pound flathead catfish. You see those protrusions from his head? Those are barbels. They sense vibration in the mud on the riverbed. But the most interesting thing about the catfish is that she really is, in some ways, one big tongue. There are taste sensors covering every part of her body, and she can build up a three-dimensional picture of the river by detecting the chemical sense of animals. So her eyes are not much use. As you can see, this river is extremely muddy, but it's the sense of taste that does the job of building up a picture of the world, and that's how he hunts, and he weighs a ton.
Oh, I can feel those teeth. Ow! I'm gonna let go. Alright, you. Go on.
The sensory world of the catfish is a remarkable one. Its map of its universe is built from the thousands of chemicals it can detect in the water. A swirling mix of tastes and concentrations, flavours and gradients. It's a world we can hardly imagine.
There's an interesting, almost philosophical point here, because it's easy to imagine that we humans perceive the world in some kind of objective way, but that's not the case at all. When you think about the catfish sees the world as a kind of swarm of chemicals in the river, or vibrations on the riverbed, whereas we see the world as reflected light of the forest, and I can hear the sounds of animals out there somewhere in the undergrowth. The catfish sees the world completely differently. So the way you perceive the world is determined by your environment, and no two animals see the world in the same way.
Like every animal, we have evolved the senses that enable us to live in our environment. But as well as equipping us for the present, those senses can also tell us about our past.
Now we have a sense of touch like the paramecium, and we have the chemical senses, taste and smell, like the catfish. But for us, the dominant senses are hearing and sight. And to understand them, you first have to understand their evolutionary history.
Why I'm in the Mojave Desert in California, to track down an animal that can tell us something about the origins of our own senses. The creature I'm looking for is easiest to find in the dark, using ultraviolet light.
Whoa! Man! Did you see that? Look at that, absolutely bizarre, glowing, absolutely bright green. Nobody has any idea what evolutionary advantage that confers.
Although they now live in some of the driest, most hostile environments on Earth, like here in the desert, scorpions evolved as aquatic predators before emerging onto the land about 380 million years ago. They've adapted to be able to survive the extreme heat that can go for over a year without food or water. And despite their fearsome reputation, 98% of scorpion species have a sting that is no worse than a bee's.
But perhaps the most fascinating thing about scorpions from an evolutionary perspective is the way that they catch their prey. You see that he spreads his legs out on the surface of the sand,
And that's because he uses his legs to detect vibrations. Scorpions hunt insects like this beetle. It's almost impossible to see them in the dark, so the scorpion has evolved another way to track them down, by adapting its sense of touch. As the insect's feet move across the sand, they set off tiny waves of vibration through the ground. If just a single grain of sand is disturbed within range of the scorpion, it will sense it through the tips of its legs. They can detect vibrations that are around the size of a single atom as they sweep past. By measuring the time delay between the waves arriving at each of its feet, the scorpion can calculate the precise direction and distance to its prey. Ability to detect vibrations and use them to build up a picture of our surroundings is something that we share with scorpions. While the scorpion has adapted its sense of touch to detect vibrations in the ground, we use a very similar system to detect the tiny vibrations in air that we call sound. And like the scorpions, ours is a remarkably sensitive system. Our ears can hear sounds over a huge range. We can detect sound waves of very low frequency at the base end of the spectrum. But we can also hear much higher pitch sounds with frequencies hundreds or even 1,000 times greater. And we can detect huge changes in sound intensity. From the delicate buzzing created by an insect's flapping wings, to the roar of an engine, which can be 100 million times louder. The story of how we developed our ability to hear is one of the great examples of evolution in action. Because the first animals to crawl out of the water onto the land would have had great difficulty hearing anything in their new environment. These are the Everglades. A vast area of swamps and wetlands that has covered the southern tip of Florida for over 4,000 years. Through the creatures we find here, like the American alligator, a member of the crocodile family, we can trace the story of how our hearing developed as we emerged onto the land. And it starts below the water, with the fish. If you're a fish, then hearing isn't a problem. You live in water and you're made of water, so sound has no problem at all travelling from the outside to the inside. But when life emerged from the oceans onto the land, and hearing became a big problem. See, sound doesn't travel well from air into water. If I make a noise now, and over 99.9% of the sound is reflected back off the surface of the water. It's because of that reflection that underwater you can hear very little from above the surface. And it's exactly the same problem that our ears face, because they too are filled with fluid. So, if evolution hadn't found an ingenious solution to the problem of getting sound from air into water, then I wouldn't be able to hear anything at all. And that solution relies on some of the most delicate moving parts in the human body. If I just drop them. Hang on a second. Oh, I've done it again. Bloody hell. Idiot. Just flipped out. These are the smallest three bones in the human body. They're called the malleus, the incus, and the stapes, and they sit between your eardrum and the entrance to your inner ear, so the place where the fluid sits. The bones help to channel sound into the ear through two mechanisms. First, they act as a series of levers, magnifying the movement of the eardrum. And second, because the surface area of the eardrum is 17 times greater than the footprint of the stapes, the vibrations are passed into the inner ear with much greater force. And that has a dramatic effect. Rather than 99.9% of the sound energy being reflected away, it turns out that with this arrangement, 60% of the sound energy is passed from the eardrum into the inner ear. Now this sound energy being reflected away, it turns out that with this arrangement, 60% of the sound energy is passed from the eardrum into the inner ear. Now this setup is so intricate and so efficient that it almost looks as if these bones could only ever have been for this purpose. But in fact, you can see their origin if you look way back in our evolutionary history. In order to understand where that collection of small bones in our ears came from, you have to go back in our evolutionary family tree way beyond the fish that we see today. In fact, back around 530 million years to when the oceans were populated with jawless fish called anathans. They're similar to the modern lamprey. Now, they didn't have a jaw, but they had gills supported by gill arches. Now, over a period of around 50 million years, the most forward of those gill arches migrated forward in the head to form jaws. And you see fish like these, the first jawed fish in the fossil record, around 460 million years ago. And there, at the back of the jaw, there is that bone, the higher mandibular, supporting the rear of the jaw. Then, around 400 million years ago, the first vertebrates made the journey from the sea to the land. Their fins became legs, but in their skull and throat, other changes were happening. The gills were no longer needed to breathe the oxygen in the atmosphere, and so they faded away and became different structures in the head and throat. And that bone, the hyomandibular, became smaller and smaller until its function changed. It now was responsible for picking up vibrations in the jaw and transmitting them to the inner ear of the reptiles. And that is still true today of our friends over there, the crocodiles.
Once more with alligator.
But even then, the process continued. Around 210 million years ago, the first mammals evolved. And unlike our friends the reptiles here, mammals have a jaw that's made of only one bone. A reptile's jaw is made of several bones fused together. So that freed up two bones, which moved and shrank and eventually became the malleus, the incus and the stapes. So this is the origin of those three tiny bones that are so important to mammalian hearing. It's quite big, isn't it? Is a most wonderful example of the blind, undirected ingenuity of evolution, that it's taken the bones in gills of fish and converted them into the intricate structures inside my ears that efficiently allow sound to be transmitted from air into fluid. It's a remarkable thought that to fully understand the form and function of my ears, you have to understand my distant evolutionary past in the oceans of ancient Earth. All sensing has evolved to fulfill one simple function: to provide us with the specific information we need to survive. And nowhere is that clearer than in the sense of vision. Almost all animals can see. 96% of animal species have eyes. But what those eyes see varies enormously. So with an animal like the mantis shrimp, you have to ask what it is about its way of life that demands such a complex visual system. Got to be very quick and very careful with this. Let him out. The complex structure of the mantis shrimp's eyes give it incredibly precise depth perception. We have binocular vision. We look with two eyes from slightly different angles and judge distance by comparing the differences between the two images. Each of the mantis shrimp's eyes has trinocular vision. Each eye takes three separate images of the same object. Comparing all three gives them exceptionally precise range finding, and they need that information to hunt their prey. Despite appearances, he's a dangerous animal. He has one of the hardest punches in nature. Those yellow appendages you can see on the front of his body are called raptoral appendages. They're actually highly evolved front legs, and they can punch with tremendous force. The mantis shrimp's punch is one of the fastest movements in the animal world. Slowed down by over 1,000 times, we can clearly see its power. It can release its legs with the force of a bullet. In the wild, they use that punch to break through the shells of their prey. But it could easily break my finger. The need to precisely deploy this formidable weapon is one of the reasons the mantis shrimp has developed its complex range-finding ability. And that punch can also help explain their sophisticated colour vision, because the coloured flashes on their body warn other mantis shrimp that they may be about to attack, while other colour signals have a quite different meaning. And yet reading these signals in the ocean can be surprisingly difficult. In the deep ocean, colours shift from minute to minute, from hour to hour, with changing lighting conditions, changing conditions in the ocean. But it's thought that even though the light quality can change tremendously, the mantis shrimp can still identify specific colours very accurately because of those sophisticated eyes. The mantis shrimp's eyes are beautifully tuned to their needs, but they're very different from our eyes. With their thousands of lenses and complex colour vision, they have a completely different way of viewing the world. And yet there's strong evidence that the mantis shrimp's eyes and ours share a common origin. Because on a molecular level, every eye in the world works in the same way.
In order to form an image of the world, then obviously the first thing you have to do is detect light. And I have a sample here of the molecules that do that detect light in my eye. It's actually specifically the molecule that's in the black and white receptor cells in my eyes, the rods. It's called rhodopsin. And the moment I expose this to light, you'll see an immediate physical change. There you go. Did you see that? It was very quick. It came out very pink indeed, and it immediately went yellow.
This subtle shift in colour is caused by the rhodopsin molecule changing shape as it absorbs the light.
In my eyes, what happens is that change in structure triggers an electrical signal which ultimately goes all the way to my brain, which forms an image of the world.
It's this chemical reaction that's responsible for all vision on the planet. Closely related molecules lie at the heart of every animal eye. And that tells us that this must be a very ancient mechanism. To find its origins, we must find a common ancestor that links every organism that uses rhodopsin today. We know that common ancestor must have lived before all animals' evolutionary lines diverged. But it may have lived at any time before then.
So what is that common ancestor? Well, here's where we approach the cutting edge of scientific research. The answer is that we don't know for sure, but a clue might be found here, in these little green blobs, which are actually colonies of algae called volvox.
We have very little in common with algae. We've been separated in evolutionary terms for over 1 billion years. But we do share one surprising similarity. These volvox have light-sensitive cells that control their movement. And the active ingredient of those cells is a form of rhodopsin, so similar to our own that it's thought they may share a common origin.
What does that mean? Does it mean that we share a common ancestor with the algae, and in that common ancestor the seeds of vision can be found?
To find a source that may have passed this ability to detect light to both us and the algae, we need to go much further back down the evolutionary tree. First living things to evolve on the planet. And it's thought that the original rhodopsins may have developed in these ancient photosynthetic cells. So the origin of my ability to see may have been well over 1 billion years ago in an organism as seemingly simple as a cyanobacterium. The basic chemistry of vision may have been established for a long time, but it's a long way from that chemical reaction to a fully functioning eye that can create an image of the world. The eye is a tremendously complex piece of machinery built from lots of interdependent parts, and it seems very difficult to imagine how that could have evolved in a series of small steps. But actually, we understand that process very well indeed. I can show you by building an eye. The first step in building an eye would be to take some kind of light-sensitive pigment, like rhodopsin for example, and build it onto a membrane. So imagine this is such a membrane with the pigment cells attached. Then immediately you have something that can detect the difference between dark and light. Now the advantage of this arrangement is that it's very sensitive to light. There's no paraphernalia in front of the retina to block light. But the disadvantage, as you can see, is that there's no image formed at all. It just allows you to tell the difference between light and dark. But you can improve that a lot by adding an aperture, a small hole in front of the retina. So this is a movable aperture, just like the sort of thing you've got in your camera. And now, you can see that the image gets sharper. But the problem is that in order to make it sharper, you have to narrow down the aperture, and that means that you get less and less light, so this eye becomes less and less sensitive. So there's one more improvement that nature made, which is to replace the pinhole, the simple aperture, with a lens. Look at that. A beautifully sharp image. The lens is the crowning glory of the evolution of the eye. By bending light onto the retina, it allows the aperture to be opened, letting more light into the eye, and a bright, detailed image is formed. Because like a camera, they consist of a single lens that bends the light onto the photoreceptor to create a high-quality image of the world. But that has a potential drawback, because to make sense of all that information, we need to be able to process it. Each one of my eyes contains over 100 million individual photoreceptor cells. I mean, that's about 5 or 10 times the number in the average digital camera. So if my visual system worked by just taking a series of individual still images of the world and transmitting all that information to my brain, then my brain will be overwhelmed. It's just not practical. So that's not what animals do. Instead, their visual systems have evolved to extract only the information that's necessary. And this is wonderfully illustrated in the toad. The toad has eyes that are structurally very similar to ours. But much of the time, it's as if it isn't seeing anything at all. It seems completely oblivious to its surroundings. Until something, like a mealworm, takes its interest. If you think about what's important to a toad visually, then it's the approach of either prey or predators. So the toad's visual system is optimised to detect them. So there, we put a worm in front of the toad, and did you see that? Incredibly quickly, the toad ate the worm. As soon as the mealworm wriggles in front of the toad, its eyes lock onto its target. Then it strikes in a fraction of a second. It's an astonishingly precise reaction, but it's also a very simple one, because the toad is only focusing on one property of the mealworm, the way it moves. These 1970s lab tests show how a toad will try and eat anything long and thin, but only if it moves on its side, like a worm. And that's because the toad has neural circuits in its retina that only respond to lengthwise motion. If instead the target is rotated into an upright position, the toad doesn't respond at all. At first sight, the visual system of the toad seemed a little bit primitive and imperfect. And it is true that if you put a toad in a tank full of dead worms, it'll starve to death because they're not moving, so it doesn't recognise them as food. But it doesn't need to see the world in all the detail that I see it. What it needs to focus on is movement, because if it can see movement, then it can survive, because it can avoid predators and it can eat its prey. I suppose in a sense, if it moves like a worm in nature, then it's likely to be a worm. This ability to simplify the visual world into the most relevant bits of information is something that every animal does. We do it all the time. We also have visual systems that detect motion. Others identify edges and faces. But extracting more information takes more processing power. That requires a bigger brain. And to see the results of this evolutionary drive towards greater processing power, I've come to the heart of metropolitan Florida. You know, it may not look like it, but underneath this flyover, just out in the shallow water, it's one of the best places in the world to find a particularly interesting animal. It's an animal that's evolved to make the most of the information its eyes can provide.
Well, what we're going to do is try and hunt some octopus. And it's, as you say in physics, not trivial. Because they developed a beautiful way of camouflaging themselves. They change colour, they have cells in their skin that change colour to match their surroundings, a stability that we don't possess, of course. They make them difficult to find. There he is, look. He went flying into there, and a crab and a load of fish went flying out, and look at his ink. There's defence mechanism. I don't know where he is, he's hiding somewhere in there. Oh. Yeah, look at those colours. What a remarkable creature.
Although the octopus is a mollusk, like slugs and snails, in many ways it seems more similar to us.
Whoa!
It's believed to be the most intelligent invertebrate.
Like he held his fist up. Look at that.
Its brain contains about 500 million nerve cells, about the same as a dog's.
What are you doing? You know, you want an example of an alien intelligence here on Earth. That would surely be it.
And it's used that brain to develop some remarkable abilities. It's become a skilled mimic. It can rapidly change not only its colour, but its shape to match the background. Some species even do impressions of other animals. They become cunning predators and adept problem solvers. They've even been reported to use tools. All these skills are signs of great intelligence, but they also rely on an acute sense of vision.
Staying the surroundings, checking us out. Camera eyes, just like mine, and they're vitally important for allowing the octopus to live the lifestyle it does. It's a visual animal, in the same way that I'm a visual animal.
The octopus is one of the only invertebrates to have complex camera eyes. Like our eyes, they capture detailed images of the world, and their brains have evolved to be able to extract the most information from those images. The optic lobes make up about 30% of the octopus's brain. The only other group that is known to devote so much of its brain to visual processing is our group, the primates, the most intelligent vertebrates.
I think it's a fascinating thought that intelligence is a result of the need to process all the information from those big complex eyes.
What's so compelling about the octopus's intelligence is that it evolved completely separately to ours. We last shared a common ancestor 600 million years ago, an ancestor that had neither eyes nor a brain. But we both evolved sophisticated camera eyes and large, intelligent brains. It suggests a tantalizing link between sensory processing and the evolution of intelligence. Sensing has played a key role in the evolution of life on Earth. The first organisms were able to detect and respond to their immediate environment, as paramecia do today. But as animals evolved and their environments became more complex, their senses evolved with them, developing the mechanisms to let them decode vibrations and detect light, allowing them to build three-dimensional pictures of their environments, and stimulating the growth of brains that could handle all that data. But for one species, the desire to gather more and more sensory information has become overwhelming. That species is us. This is the closest thing to hallowed ground that exists in a subject that has no saints, because That telescope is the one that Edwin Hubble used to expand our horizons, I would argue, more than anyone else before or since. In 1923, Edwin Hubble took this photograph of the Andromeda Galaxy. You can see his handwriting on the photograph. He did it by sitting here night after night for over a week, exposing this photographic plate. Now at the time, it was thought that this misty patch you see in the night sky was just a cloud, maybe a gas cloud in our own galaxy. But Hubble, because of the power of this telescope, identified individual stars, and crucially, he found that it was way outside our own galaxy. In other words, Hubble had discovered this is a distant island of stars. We now know it's over 2 million light years away, composed of 1 trillion suns like ours. Hubble demonstrated that there's more to the universe than our own galaxy. He extended the reach of our senses further than we could have imagined. With the help of the telescope, we could perceive and comprehend worlds billions of light years away. There's a wonderful feedback at work here, because the increasing amounts of data delivered by our senses drove the evolution of our brains, and those increasingly sophisticated brains became curious and demanded more and more data. And so we built telescopes that were able to extend our senses beyond the horizon and showed us a universe that's billions of years old and contains trillions of stars and galaxies. Our insatiable quest for information is the making of us. In 2009, a new species of spider was identified. A spider with superpowers. It was named exactly 150 years after the publication of Darwin's On the Origin of Species, in which he explained why life on Earth is so diverse and so complex. Darwin's theory of evolution by natural selection was built on the work of naturalists who were discovering thousands of new species across the world. That process of finding species new to science and naming them continues to this day, and it's recognised in the name of this newly discovered arachnid, Darwin's bark spider. The spider occupies a unique niche. It can hunt where no other spider can. That spider creates the largest webs found anywhere on Earth, and in order to do that it has to produce the strongest silk of any spider. They can span over 25 metres across lakes and rivers, and actually no one knows how they get their webs across such a large distance. But Darwin's bark spider is just one of thousands of unique species of animals and plants that you find in Madagascar. The rainforests here are one of the most biodiverse places on the planet. And each year, more discoveries are made as researchers try to understand why this tiny corner of the universe is so prolific. All of these living things were found within a 5-minute walk of this field station, and the diversity is remarkable. There's a chameleon there. These are orchids. This big green leaf is a traveller's palm. There are 4 species of mushroom on that branch alone. Across Madagascar, there are over 14,000 species of plants. There are hundreds of species of mammals and birds and reptiles, and over 90% of them are unique to this island. How could it be that so many diverse living things, so beautifully adapted to their environment, could have emerged from a universe that's governed by a simple set of natural laws? The fact that we know the answer to that question is one of the greatest achievements in science. In this film, I want to explore how these endless forms, most beautiful, have emerged from a lifeless cosmos. Africa, a whole continent full of creatures utterly different from those in Madagascar. But the diversity of life doesn't stop at what you see, because within each individual lies another hidden world of complexity. This, believe it or not, is the top predator in Africa, or she will be when she's older. She's only about 8 weeks old now. Her body is built from a host of different molecules, and by far the most diverse group are known as proteins. You can see the proteins here. Those claws, so vital for the lion's survival, are made of a protein called keratin. Her eyes, also absolutely vital for survival, have a protein called opsin, which is bound to a pigment to make structures called rhodopsins, which allow her to see in colour and also allow her to see very well at night when she's hungry. There are also proteins in her muscles. Myosin and actin, which are the things that allow her to run away. The proteins in a lion come in countless different forms, but they all share something in common: a backbone of carbon, an atom that's able to form long, complex molecules. Of all the 92 elements, there really is only one that has that appetite for bonding its 4 electrons to share them with other molecules. Carbon will share those electrons with nitrogen, with oxygen, with hydrogen, and critically with other carbons to build up these immensely complex chains, the amino acids and the proteins, which are the building blocks of life. So to understand our planet's endless diversity, we must begin by considering this life-giving element.
I've got a few scratches now because of you, because of your proteins.
After all, to build a lion, you must first build carbon. And that's a story that stretches back to a time long before there were even stars in the universe. $13.5 billion years ago, just a few 100 million years after the Big Bang, the universe was a carbon-free zone. An infinite, sterile gloom of hydrogen and helium clouds. Until one day, those vast clouds began to collapse under the force of gravity. And long before the solar system, Earth, all life existed. The first stars were born. Stars did much more than just illuminate the universe, because that set in train a sequence of events which ultimately is necessary for the existence of life in the universe. And we can still see that process playing out in the universe today. This is the brand new South African Large Telescope. Its mirror is 11 meters wide, making it the largest optical telescope in the Southern Hemisphere. And it recently helped to pin down what's happening in an object some 650 million light years from Earth. System is known simply as the bird. It's the spectacular result of what we used to think were 2 galaxies colliding. This beautiful, almost lifelike system is known simply as the bird. It's the spectacular result of what we used to think were 2 galaxies colliding. It's events happening in the head of the bird that are the most interesting from the perspective of life in the universe, because the head is formed by another galaxy, a 3rd galaxy, an island of billions and billions of stars colliding with the 2 galaxies that form the wings and the body at a speed of around 250 miles a second. Now, the turbulence, the disturbance that creates is causing many new stars to be formed. These stars begin their lives by burning hydrogen to produce ever more helium. But as they age, as the hydrogen runs out, they turn to this helium. The temperature at their core rises, increasing the chances of 3 helium nuclei fusing together to form a new element, carbon. That process has been going on for almost the entire history of the universe, back 13 billion years, and it's the formation of stars that is the vital first step in the formation of life, because stars produce the heavy elements in the universe, including carbon. From the universe's earliest times, Carbon has been created inside aging stars. And over time, this carbon has built up, drifting through the cosmos as dust, until some of it was caught up in the formation of a planet called Earth. And it's here that we can see this ancient carbon brought vividly to life.
Today, the universe is old enough that countless stars have lived and died, and so there's been plenty of time to synthesize the primordial hydrogen and helium into the heavy elements. The question now is, how does that carbon get into the web of life? Well, today it enters via one ingredient, and I'm going to measure it using this balloon. The ingredient is carbon dioxide, which plays a key role in photosynthesis. Each night, the carbon dioxide concentration increases, filling the air around the leaves at the top of the trees. Now, this balloon has a carbon dioxide monitor in it, which is going to measure the change in the levels of CO2 at the top of the forest canopy as night turns to day. As the sun rises, the trees begin to photosynthesize. Now, at 6 p.m. last night, so just after sunset, the concentration was around 350 parts per million. Around 10 p.m, so 4 hours after sunset, the concentration had risen to about 400 parts per million. And now, at about midday, the concentration is back down to about 3, 4, 5 parts per million. So that's a variation over a period of 18 hours of, around 10% in the concentration of carbon dioxide just in that piece of atmosphere at the top of the forest canopy. So what you're seeing there is photosynthesis in action. Every day across the planet, photosynthesis uses sunlight to turn carbon dioxide and water into simple sugars. The overwhelming majority of the carbon is locked up inside long chains of sugar, molecules called cellulose and lignin. Now, lignin is the stuff that gives wood its strength. So in this form, and remember, that is most of it, it is very difficult indeed for animals to access. For the energy and nutrients locked away inside these long carbon chains to move through the food web, they must be broken down. And the best place to see that process in action is out on the open plain. It's one vast larder for all manner of organisms. But by far the most effective harvester of carbon is actually one of the smallest creatures on the savannah. Termites are social insects working together to form a characteristic site seen all over the bush. That's a termite mound. Actually, it's a tip of the iceberg. The termite city extends way beyond that underground. And its function is fascinating. It's essentially an air conditioning system. What it does is maintain very specific conditions inside the mound, the conditions of the rainforest. When the termites first colonised the savannah some 30 million years ago, they brought the rainforest with them
to support a form of life that was already wonderfully adapted to living off dead wood. And this is what these termite mounds are all about. You see those structures there, those white honeycomb-like structures. Those are called fungal combs. They're wood pulp and possibly bits of dead grass that the termites bring in and build into that structure. And the reason the conditions have to be the same as the rainforest, they grow a particular genus of fungus called Termitomyces around those honeycombs. The job of that fungus is to break down the lignin and the cellulose inside the wood and convert it into a form that the termites can eat, which actually you can see there, there are little white nodules just present on the honeycomb structure. The termites lack the enzymes to break down the wood efficiently, so they've become farmers, tending to one giant social stomach. So there's a very intense relationship between the termite and the fungus. You don't find that fungus anywhere else, actually in the world, as far as we know, other than inside termite mounds. And it's thought that up to 90% of the carbon locked up in lignin in this part of Africa is released back into the food chain again, solely by those termites and that fungus. So the termites deal with most of the lignin, but that still leaves a vast store of carbon in the form of cellulose. Across Africa, herds of mammals graze on grasses and leaves, turning this cellulose into meat. Many are a type of mammal known as a ruminant, the largest of which is one of the easiest animals to spot on safari.
Giraffe as well.
Giraffes live off a diet that's similar to termites. They eat cellulose, primarily actually the tops of the acacia trees that you see here scattering the African savanna. And they face that same problem. They've got to break those difficult carbon bonds down. And they've come up with a very similar solution, which is to cultivate bacteria and fungi. They do it inside their stomachs, and ruminants, like giraffes, have had to build a very complex system in order to do that. They've got 4 stomachs. One of them contains their culture of bacteria and fungi, and they allowed them to digest that difficult cellulose. Even with all this hardware, ruminants must feed for over 2/3 of the day. But there are other creatures here that have found a shortcut. After all, if plant fibres are hard to digest, why not let someone else do the work and simply steal a meal?
Come here first. God. Look what we've just found. We were out looking for giraffe this morning. We've found about 10 of them just over there. But in looking for the giraffe, we've just found a leopard. This is one of the top predators out here. He's got very little to fear, apart from other leopards and maybe lions. He's having a good look. He certainly doesn't care about us. He's around 2 years old, and at the moment he doesn't have his own territory. He's too young for that, and so he's lying low. He'll have to make about 2 kills a week to stay in good condition, so maybe catch an impala every 3 or 4 days. And he's obviously doing that because look at him. Now he's looking for protein, and I'm a little bit worried because I'm protein. Oh, wow. He's coming really close to us because he's after the Sandman's poon pole, which is it's incredible. My God.
From its origin in the death of stars, its capture by plants, through insects, mammals and on. The carbon cycle is the real circle of life. Out there tonight, the relentless recycling of carbon through the food chain will continue. As night falls, you can almost sense it, a change in the sounds and the atmosphere. Some will die so that others can live, as carbon leaps from branch to branch across the great tree of life. And guiding it on its way is just one very special form of chemistry. Every living thing is just a temporary home for carbon atoms that existed long before there was life on Earth and will exist long after Africa and Earth are gone. Of life, the information needed to build a zebra or a tree or a human being or a lion persists. It's passed on from generation to generation in a molecule, a helical molecule with a backbone of carbon called DNA. There was a time when Earth years ago, life was already underway in the form of tiny living specks that probably all shared the same biochemistry. We know that every living thing on the planet today, so every piece of food you eat, every animal you've seen, everyone you've ever known or will know, in fact every living thing that will ever exist on this planet was descended from that one universal common ancestor, or Luca. So, just as the universe had its origin at the Big Bang, all life on this planet had its origin in that one moment. less than 1 billion years after its formation, there was already life on Earth. It's possible that some of it used biochemistry utterly different from the life we see today. If so, it has long been extinct. It's also possible that the first life may not have been cellular, just living chemistry in the porous rocks of some ancient ocean. We're not sure, but what's certain is that one day a population of organisms showed up with biochemistry that we would recognise. This was Luca, the first expression of a form of life that would, in time, throw up a group of humans who left their mark in this part of Africa. Now, we don't know what Luca looked like. We don't know precisely where it lived or how it lived. But we do know this. If you start to trace my ancestral line back to my parents, to their parents, to their parents, to their parents, all the way back through geological timescales over hundreds of thousands and millions and billions of years, there will be an unbroken line from me all the way back to Luca. We know that because every living thing on the planet today shares the same biochemistry. We all have DNA. It's made of the same bases, A, C, T, and G. They code for the same amino acids. Those amino acids build the same proteins which do very similar jobs, whether you're a plant, a bacterium, or a bipedal hominid like me. So all life uses the same fundamental biology. Those 4 bases, A, C, G and T, which code for just 20 amino acids, which in turn build each and every one of life's proteins. Be you bacteria, plant, bug or beast, your design comes from your DNA. So it's this molecule that must hold the key to understanding why life today is so diverse. We now know that the answer to the question, why is life on Earth so varied, is actually the answer to the question, why is the DNA molecule itself so varied? What are the natural processes that cause the structure of DNA to change? Well, part of the answer actually doesn't lie on Earth at all. It lies up there amongst the stars. And I can show you what I mean using this, which is the cloud chamber, a piece of apparatus that has a unique place in the history of physics. I'm going to cool it down using dry ice, frozen carbon dioxide, just below minus 70 degrees Celsius. Put the top on. Hear that? That's the metal at the bottom of the tank cooling down very rapidly to minus 70. The cloud chamber works by having a supersaturated vapour of alcohol inside the chamber. Plenty on there. Now, I want to get that alcohol, I want to boil it off to get the vapour into the chamber, so I'm going to put a hot water bottle on top. I mean, this is the first genuine particle physics detector. It's the piece of apparatus that first saw antimatter, and it really does consist only of a fish tank, some alcohol, a bit of paper and a hot water bottle. There, look at that. You can see that cloud, that vapour trail. That's a cosmic ray. That was initiated by a particle, probably a proton, that hit the Earth's atmosphere. it almost certainly originated outside our solar system and was accelerated by the magnetic fields of our galaxy. It may even have begun its life beyond our galaxy. Now, imagine if one of those hits the DNA of a living thing. What that will do is cause a mutation. That mutation may be detrimental, or very, very occasionally, it might be beneficial. And I think it's quite wonderful to imagine that maybe one of the key mutations that was selected for over the millennia that led to some trait in me was caused by some particle that began its life perhaps in a massive supernova explosion, perhaps outside our galaxy, and went and hit the DNA of something and caused some kind of beneficial mutation. We don't know, but you can dream, can't you?
Mutations are an inevitable part of living on a planet like Earth. They're the first hint at how DNA and the genes that code for every living thing change from generation to generation. Mutations are the spring from which innovation in the living world flows. But cosmic rays are not the only way in which DNA can be altered.
There's natural background radiation from the rocks, there's the action of chemicals and free radicals, there can be errors when the code is copied, and then all those changes can be shuffled by sex, and indeed whole pieces of the code can be transferred from species to species. So bit by bit, in tiny steps from generation to generation, the code is constantly randomly changing.
Now, whilst there's no doubt that random mutation does alter DNA, evolution is anything but random. It can't be, because the chances of something with DNA as complex as this appearing by luck alone are vanishingly small.
Imagine you just changed one position in the code at random, a random mutation. There are 4 letters, A, T, C and G, so there are 4 possible combinations. If there are 2 places in the code, there are 4 combinations for each one, so that makes 16. If there are 3, then there are 64 possibilities. By the time you get to a code with 150 letters in it, then there are more possible combinations in the code than there are atoms in the observable universe. Now, a hippo has a code with around 3 billion different letters. So the number of combinations of those letters, the chances of producing that code at random are absolutely infinitesimally small. It's impossible.
So there must be a non-random element to evolution, a natural process which greatly restricts this universe of possibilities and shapes the outcome. We call it natural selection. And to see it in action, let's return to where we began, on the island of Madagascar.
Around 65 million years ago, a group of seafarers were nearing the end of a long journey
across the Indian Ocean. These were accidental travellers, a group of creatures from Africa, trapped on a natural raft and carried by the ocean currents. The land they found was virgin green territory. Plants, insects, reptiles and birds had established themselves, but there were none of their own kind. They were caught up in a saga that tells of the great shifting of Earth's continental plates. It's impossible to understand the diversity of life on Earth today without understanding the shifting geography of our planet. See, here's a map of Earth's southern hemisphere as it was 150 million years ago, and you see it's dominated by a single landmass called Gondwana. And then 90 million years ago, Gondwana had begun to break up, to separate into something that looks quite recognisably like Africa. And these two islands, Madagascar and India, now subsequently India has drifted northwards and bumped into Eurasia, raising the Himalayas. But crucially, Madagascar has remained isolated. It's been an island surrounded by ocean for almost 90 million years. So when those seafarers arrived on their raft of trees and twigs and leaves, they had a blank canvas. This 2, 3, maybe even a single pregnant individuals had a whole island to roam across, and over 65 million years they have blossomed into hundreds and thousands of individuals and become Madagascar's most iconic animals. Finding the descendants of those ancient mariners is not easy, but local guide Joseph has been tracking them for years and is going to help me find them. There at the top of the tree is an indri, which is the largest lemur in Madagascar. And I've just sat there watching this quietly at the moment. This lemur here is a very special lemur. He has a name, he's called David. After Sir David Attenborough. I can only do this because Joseph has spent a lot of time with these lemurs, so they trust him, and therefore it seems they trust me. It's enormous, huh? The reason it's thought that we find lemurs here in Madagascar alone, is because there are no simians, there are no chimpanzees, none of my ancestral family dating back tens of millions of years to outcompete them. So what's thought happened is that around 65 million years ago, one of the lemur's ancestors managed to sail across the Mozambique Channel, landed here. There were none of those competitors here, and so the lemurs have flourished ever since. There are now over 90 species of lemur or subspecies in Madagascar. No species of my lineage, the simians. Over a vast sweep of time, the lemurs have diversified to fill all manner of different habitats. From the arid, spiny forests of the south to the rocky canyons in the north, there is something about this island that is allowing the lemur's DNA to change in the most amazing ways. We're on the hunt for an aye-aye, the most closely related of all the surviving lemurs to their common ancestor. Oh yeah, yes. His absolutely two bright red eyes shining out very high up in the nest. On the side of her in this forest, which is very dark and dense. The team have located a female aye-aye and her son. They want to attach radio collars to track their movements and better understand how far they range through these forests. But first, they must sedate them with a dart. What I'm going to do is wait for it to come down low enough to get that clean shot. I mean, how do you get a clean shot in this? I have no idea. After 2 hours of traipsing through the treacherous forest, the aye-ayes remain at large.
Oh yeah! I know. Well, here is the aye-aye that was tranquilised last night. They finally got her about half an hour after we left. I think it was probably because we were disturbing her. Apparently, as soon as we'd gone, she came down the tree and she was tranquilised. And as you can see, she's pretty well sedated now, which is fortunate for me because she has certain adaptations that I wouldn't like to be deployed. You can see there the teeth. The teeth are very unusual for a primate. In fact, unique because they carry on growing. So she's much more like a rodent in that respect. And that's so she can gnaw into wood. See, aye-ayes have filled a unique niche on Madagascar. It's a niche that's filled by woodpeckers in many other areas of the world. What she does is she feeds on grubs and bugs inside trees. And to do that, she has several unique adaptations, of which her teeth are one. The most startling is this central finger here. It's bizarre. It's got a ball and socket joint for a start. So it has complete 360-degree movement. It feels to me almost as if it's broken, but it isn't. It's just, you can move it around in any direction. And she uses that finger initially to tap on the trunk of the tree. And then listening to the echo from that tapping with these huge ears. She can detect where the grubs are, and then she gnaws through the wood with those rodent-like teeth, and then uses this finger again to reach inside the hole and get the bugs out. So the question is, why? How could an animal be so precisely adapted to a particular lifestyle? She's waking up now. And the answer is natural selection. See, what must have happened is way back when the ancestors of the lemurs, the lemuriforms, arrived in Madagascar, there must have been a mutation that lengthened the middle finger ever so slightly of one of those lemurs, and that must have given it an advantage. That must have allowed it perhaps to reach into little holes and search for grubs. There's some reason why that lengthened middle finger meant that that gene was more likely to be passed to the next generation and then down to the next generation. So that landscape of possibilities is narrowed. It's narrowed because that gene persists. And it's persisted now for at least 40 million years, because this species has been on one branch of the tree of life now for over 40 million years. And so, over those years, that middle finger has got more and more specialised.
Natural selection has allowed the II's wonderfully mutated finger to spread through the population. And this same law applies to all life. If you have a mutation that helps you in the struggle to survive, you are more likely to leave more offspring. And in the next generation, that mutation is more likely to survive.
So this animal is a beautiful example, probably one of the best in the world, of how the sieve of natural selection produces animals that are perfectly adapted to live in their environment.
Now, there are many reasons to study the II, but here's a good one. In the 1970s it was thought the II was extinct. Now we know there are several thousand in the forest of Madagascar, 5, 6, 7,000, certainly less than 10,000. But over the last 50 years, 50% of this forest has vanished. This is an animal that's been around as a species for over 40 million years. So it's important to know how these animals are doing and how they're surviving in this diminishing habitat.
Whilst natural selection explains how the II evolved, it alone can't explain how a small group of individuals over 60 million years ago gave rise to over 90 different species of lemur today. But there is another form of life that can offer us a clue.
Up here in the high forest canopy, we're in a very different environment to the one down there on the forest floor. It's a more arid environment. It's almost like a desert. It's exposed to the sun. Water is harder to come by. And so this is a sea of different niches that are able to be occupied and exploited by animals that are different to the ones you'll find down there on the floor. So in a very real sense, this is an island to be colonised.
And sure enough, there are settlers to be found, even here.
You see that thing that looks like a muddy ball there on the branch? Well, that's an ant's nest. It's home to a species of Chromatogaster ants that are unique, not only to Madagascar, but to the forest canopy.
You see, what makes those ants unique is that they can build their own nests. There are very few species of ants that can do that. So that is an island, that is a niche, and it's allowed that species of ant to develop because they're isolated from the rest of the ecosystem. And astonishingly, within this niche, another form of life new to science has been discovered. A beetle that manages to survive here unharmed by the ants. How it does it is a mystery. But what is known is that this particular species has only ever been found inside these nests. So that really is its own mini ecosystem, with species living in it that are unique to that island. We live on an ever-shifting, dynamic world that creates islands in abundance. Earth's mountain ranges, river valleys and canyons all create islands for life. And it's these islands that those ancestors of the lemurs found when they arrived in Madagascar. Empty niches where populations became isolated and over great swathes of time evolved into such wonderfully diverse forms. Years on from the origin of species, the subtlety and beauty of Darwin's insight is still revealing itself to us. It describes how our beautiful, complex tree of life has grown from a once desolate universe. The chemistry of carbon allows for the existence of a molecule that is able to replicate itself and pass information on from generation to generation. There can be random changes in the structure of that molecule, mutations, and they're tested by their interaction with the environment and other living things. The ones that pass that test survive, and the ones that fail that test are lost. The separation and isolation of living things onto islands, which may be physical, like Madagascar, or just a single branch of a single tree, results in speciation, the explosion of living forms highly specialised to occupy niches within niches. And this is the explanation for the diversity of life on Earth. There is grandeur in this view of life, as Darwin wrote, and understanding how it happened surely only adds to the wonder. As precise as Einstein's theories of relativity and as profound as thermodynamics, Darwin has given us another universal law. Evolution by natural selection. And if evolution is the law on this island, then it will apply throughout the cosmos. Which begs a big question. Could there be other trees of life most beautiful amongst the stars? In 2011, we discovered a rocky planet orbiting around a distant star with daytime temperatures not too dissimilar to those found on Earth. Now, there must be millions, if not billions, of such planets out there in the universe, and it's inconceivable to me that none of them will have trees of life as complex or even more complex than our own. But that doesn't devalue the existence of our tree, because our tree is unique. It consists of thousands of branches, all interdependent on thousands of others, and the precise structure depends on chance events, like the passage of the lemurs across the ocean 65 million years ago. So when you go outside tomorrow, just take a look at a little piece of your world, a corner of your garden, or a park, or even the grass that's growing in a crack in the pavement, because there will be life there, and it will be unique. There will be nowhere like that anywhere else in the universe, and that makes our tree, from the sturdiest branch to the most fragile twig, indescribably valuable.
Stay with BBC HD tonight for highlights of the Man U game versus Everton and Aston Villa up against West Ham. Match of the day 2 is coming up next.
Okay, we're done. I hope you learned something about painting, brushwork, and also about evolution and science and space and everything. I really love listening to science and stuff when I'm painting, because I'm learning at the same time as I do the thing I love. And maybe you should do too. Here you have the chance. Now I hope to see you on Patreon, and sign up for $5 if you'd like to support my channel, and I hope to see you in the next video.